Today we're going to talk about graphing absolute value functions. So in the past we have done some stuff with absolute values of numbers, but never have we graphed an absolute value function. So if you look up here, an absolute value function is a function that contains an absolute value expression with this parent function f of x equals absolute value of x. So what the parent function is, it's the most basic function of an absolute value family, which means there's no numbers added or subtracted or multiplied or divided within this problem. It's just the absolute value of x. So if you look over to the right, here is the graph of f of x equals absolute value of x. If you look at the absolute value function, every absolute value will form this thing that's shaped like a V. And every V has a couple different things that go with it. It has this point where the two sides kind of meet right in the middle, and that point is called its vertex. You can also graph an absolute value on your graphing calculator. So if you go to y equals, the way you get to the absolute value function is by hitting your math key. You can see your math key right here. And then you go over, right arrow over to the number button, and then you will see the words ABS. If you hit enter, either the words ABS or the absolute value symbols will show up on your calculator. Then you just put X in there, and then you can hit your right arrow and get out of that spot, and there's your absolute value of X. Before we go any further, we then have to set our window. You can either do that by just hitting the window button and changing your settings, or if you want a standard window, if you just hit zoom and then go down to Z standard 6, it will graph on a standard window, which is -10, 10, -10, 10. So here's the graph of our absolute value function. So what we are going to do today is we are going to do different things to this absolute value function. We are going to add things, subtract things, which in case then moves your absolute value up, down, left, right, makes it skinnier, makes it wider, and all sorts of things. So first thing we're going to do is take a look at the vertex form of an absolute value function. If you take a look right here, the vertex form is written like this, where A is just a number written out front, and then you have either an X minus an H, or it could also be a positive in there, and then you have a plus or minus K at the end. So what we're going to do is we are going to take this function and do all sorts of things to it to get a new function that is also part of the family of the absolute values. So the first thing we're going to look at is what happens if we add a number out back. So if I take a look and I graph that as well, if I go down to y2 and I put in my absolute value of x there, but I add a number, say we add 3. If I graph that function, you will quickly notice is that when I add a number out back, what it does is it moves it up. So an example of that would be if I had f of x equals x plus 3, the way that would be translated is it would move the absolute value of x up 3. And sometimes they will call that a vertical translation up 3. So the vertical translation just means it moves up or down. So if the plus number out back moves it up, you can probably guess what the minus number out back does, and that moves it down. So if I had f of x equals absolute value of x minus 3, that would actually move the absolute value function down 3. Let's try a different one. So now if we look at inside, so say I go back here, and instead of putting the plus out back, I now have a plus 3 inside. If I were to graph that, there's my original one. If you notice, the new one was actually moved left 3. So it's kind of crazy, but inside, whenever something is inside, you actually do the opposite. So this actually moves it left. And if I did an example and had an x plus 3 in there, I would say it is moved left 3. Which means if there's a minus inside, that moves it right. So if I had f of x equals absolute value of x minus 3, that would move the absolute value right 3. Again, we called this a vertical translation. This is actually a horizontal translation. So if you ever see the words horizontal translation, right 3, that just means you move it to the right. Let's now go back and look to see what happens when there's a number out front. So in this case, I'm going to put a 3 out front instead. So I'm going to graph the absolute value, or 3 absolute value of x. There's my original, and there's my new. This time, if you notice, what it does is it makes it skinnier. So whenever there's a number out front and that number is greater than 1, it really makes it skinnier. However, we don't necessarily call that skinnier. We call that a vertical stretch. So an example of that would be, if I had the 3 out front, what I would say is that is a vertical stretch of 3. Whenever we do vertical stretches or shrinks, we always include the number with it. So what if the number is not greater than 1? If the number is between 0 and 1, what it actually does is it makes it, instead of skinnier, it makes it wider. So that is actually called a vertical shrink. So an example of that might be f of x equals 1/3 absolute value of x, and that is called a vertical shrink of 1/3. Okay, the next thing we're going to look at is when there's a number inside. Remember how up here we said whenever the number is inside, it's the opposite? It is the same thing here. So if the number is greater than 1 and the number is out front, it's a vertical stretch. However, if the number's inside, it is the opposite. So instead of a stretch, this would actually be a shrink. And instead of it being a vertical shrink up and down, it's actually going to be a horizontal shrink. So for example, if I put the 3 inside the absolute value, that would actually be a horizontal shrink. But instead of 3, you actually flip that and get it 1/3. If the number is between 0 and 1, it is the opposite, so it's actually a horizontal stretch. So an example of that would be, is if I had a 1/3 inside, that would actually be a horizontal stretch of 3. All right, we have one last thing to do. The last thing deals with the negatives. If there is a negative out front, what it does is, I'll show you real quick here. So if you will look, what it does is it flips it over your x-axis. So if there's a negative out front, it is a reflection over the x-axis. And if the negative is inside, it's a reflection over the y-axis. So just for kind of a practice, what an example of a problem might look like is if you had something like this. You would have to tell me what has happened to your absolute value function with all of these different pieces to it. So what you would do first is you come across a negative. The negative is out front, so we know that it is a reflection over the x-axis. Then there's a 3 out front. A 3 out front, it's greater than 1, so that means there is a vertical stretch of 3. The +2 inside, +2 means it's moved left, so this is left 2, or a horizontal translation left 2. And then the -5, minus out back means down, so this is moved down 5. And then what you can do is we can actually kind of graph them both and see if we're right. So I have -3. Lift it up a little for you to see. So I have -3 math over to number. Inside there I go x + 2. Outside I go -5. So if you hit our first one, our graph, here's our first one. This one is a reflection over the x-axis, which means it opens down. It stretches by 3, which means it's skinnier. The vertex is moved left 2 and down 5, and you can see our graph. Okay, so now we are going to talk about how to graph some of these. So we're not going to do them all on this page. We're just going to take a couple. And I think I'm going to take some of the harder ones at the bottom. So what we're going to do on 4, 5, and 6 is we are going to graph them, give the comparisons, the vertex, the domain, and the range. So the first thing I'm going to do is I'm going to do the comparisons. So I start by looking out front, and there's a negative out front. So the first thing I'm going to write down is that means there's a reflection over the x-axis, which means it opens down. The next thing I see is a 3. The 3 is out front, which means it is a vertical stretch of 3. It's a stretch because that number is bigger than 1. Inside, I have a -2, which is always the opposite, which means I'm going to move it right 2. And then I have a +1, which means it is moved up 1. So normally, I'm just going to kind of roughly sketch. Normally, our parent function looks like this. So what you can do is then get the vertex right away by doing these things to it. A reflection and a stretch do not move the vertex, but this does. So my vertex always starts at 0, 0. So to get my new one, I am going to then move this 0, 0 vertex right to up 1. So my vertex is at 2, 1. Okay, now to get the graph, I actually know that it's going to open down. But to get some exact points, what you can do is I'm going to clear these both out of here a minute. If you can put it in your graphing calculator, -3, math, over to number, absolute value. Inside there, I'm going to put x -2. I'm going to hit my right arrow to get out and hit +1. If I hit graph, what you will notice is that my vertex here and my vertex here are the same. Once you do that, if you go to this thing called your table right above your graph, so if I go my second blue button here and then graph, what will pop up is this table. And if I scroll on this table down to my point 2, 1, which was my vertex, I can get some nice points by graphing the coordinate above it and below it. So I'm going to graph the coordinate 1, -2. It's the point right above it, and I'm going to graph the point right below it, 3, -2. Once I have those nice coordinates, I can then complete my graph of my absolute value. I can then look and say my domain. It goes forever and ever both directions to my x. My domain is all reals. My range will always deal with the y value of my vertex or the higher low point of my vertex. That value is at 1, which will be the same as the y value here. And because it's going under, that will be less than or equal to 1. Let's try another one. First thing I see is a negative. So the first thing I write down is a reflection over the x-axis because the negative is out front. The 1/3 is out front, so I know it's a vertical because it's a fraction between 0 and 1. That is a vertical shrink of 1/3. The +1 means left 1, and the -5 is down 5. Remember, inside is always right, left. Outside is always up, down. This is always opposite. This is always what you think it should be. So I start with my vertex here. I'm moving left 1 and down 5. So my new vertex is going to be -1, -5. I am then going to go and put it in my calculator. Negative, I'm going to put my 1/3 in parentheses. Math, over to number. Absolute value of x +1, right arrow out, -5. And I'm going to hit graph. And you will notice that even though it looks a little different, their vertex is -1, -5 as well. And if you notice, the shrink has made it much wider. So now if I go to my table and I find that vertex -1, -5, I need to graph a point above it or below it. If you don't like graphing fractions or decimals, you can find a nice point above and below if that is easier. So the nice point above is -4, -6. A nice point below that vertex is 2, -6. And once I have those two dots on my graph, I can then draw my picture. Domain again is reals. The domain for all absolute values will be reals. My range deals with y. The y value here is -5. because the arrows are going down, it is less than or equal to. Last one. First thing I come across is a 1/2, so that is a vertical shrink of 1/2. Plus 3 inside is left or right. When you're adding, because it's plus, it'll be the opposite, which will be left 3. Minus 4 is down 4. So my vertex moves left 3, down 4. So my new vertex is -3, -4. I can actually automatically fill in my domain, and I can fill in my range with my y and -4. So now if I go back to my calculator, I can put that in here. I'm going to put my 1/2 in parentheses, math, over to number, absolute value of x plus 3, and then I'm going to go -4, and I'm going to hit graph. So now if I look here, my vertex is at -3, -4. If I go to my table, I find that value. I graph a point above. I'm going to pick -5, -3. Graph a point below. I'm going to pick -1, -3. I'm going to connect those arrows. I then see that it opens up, so I know that y is going to be greater than or equal to -4 for my range. The last thing we're going to do is we're going to do this comparison in some equations here. So if you take a look here, what we're going to do is we're going to compare f to g and describe the transformation. So if you look here, you will notice that everything is the exact same, but this has a 2 inside. Because the 2 inside it's inside and not outside, it's going to be horizontal. Because inside is always opposite, normally it would be a stretch, but in this case it will be a shrink. And the way you get that shrink is by taking the reciprocal of that and making that shrink 1/2. Over here, we're comparing this to this. The first difference I see is that there's a 5 out front. So I would say that is a vertical stretch of 5. It's a stretch because it's bigger than 1. It's vertical because it's out front. And then the other thing I see is a +7. So that is moved up 7. The last thing we're going to do is we're going to write some equations. So we're going to take f of x equals absolute value of x, and we're going to write a new equation based on what they say. Horizontal translation 4 units to the right. So remember, whenever it's left or right, it's inside, and inside is always the opposite. So you normally think of right as positive. Because it's opposite, it will be x minus 4 inside. Okay, next one. Reflection over the x-axis. So right away, we know that a reflection over the x-axis means there's a negative out front. A vertex at -2, 7, which means, if you think about where -2, 7 is, it is moved left 2, up 7. Because it's left is inside and it's always opposite, so then inside goes x plus 2. Up 7 is always outside and it is what you think it should be, so that will be a +7. And then our last one, a vertical shrink of 1/2. Vertical shrinks are always out front, so our vertical stretches. And then 5 down. Up and down is always out back, and that will be -5.